You have pressed the log button on your calculator, in an exam, maybe in a chemistry class. You got an answer and you moved on. But here is the question nobody asked you. What did you just do? Not what the formula is. What did you actually ask when you pressed that button? To understand the logarithm, look at how exponential growth works. Exponentiation asks a forward question. Start with 10, multiply it by itself twice, and you get 100. 3 times, 1,000. 6 times, 1,000,000. The logarithm asks the exact reverse question. If you have 100, how many times must you multiply by 10 to get there? 10 to the power of what gives 100? The answer is 2. The logarithm is the exponent. That is the complete definition. When you use this function, you are isolating the number of multiplications required to reach your target. There is a precise geometric way to see this relationship. If we draw the curve for 10 to the power of x, we see it rises steeply. 1 gives 10, 2 gives 100, 3 gives 1,000. Now, look at the perfect diagonal mirror right down the middle. Reflect the curve across this diagonal line, and you get the logarithm. Every point on the exponential curve has a corresponding point on the logarithm curve. The inputs and outputs swap. The logarithm undoes the exponential. Why do we need this reverse operation? Because the universe produces unmanageable numbers. If you place 1 on a number line and 1 billion on the far right, trying to mark 1, 10, 100, and 1,000 becomes impossible. They are crushed together at the extreme edge. But apply a base 10 logarithm to every number, and the scale transforms. This operation collapses the billion-fold range into a 9-step scale. Every number is now evenly spaced, comparable, and human-sized. Logarithms are a translation tool. They make incomprehensibly large universal ranges legible to the human mind by focusing on the magnitude rather than raw value. In 1935, Charles Richter needed to measure earthquakes. The problem was that the largest earthquakes released trillions of times more energy than the smallest tremors. No linear scale could show both. This chart shows the Richter scale, which is simply a base 10 logarithm of ground movement. A minor earthquake might register as a 4. The catastrophic 2004 Indian Ocean earthquake was a 9.1. The visual difference on the scale is only 5.1, but the actual difference in ground movement is 10 to the power of 5.1. That small numeric gap hides 125,000 times more destructive energy. Your own body navigates this exact same scaling problem. Your ears can detect a whisper, which is a tiny pressure change, but they can also withstand the roar of a jet engine, a pressure change a trillion times larger. This vertical chart maps that trillion-fold sound pressure range onto the decibel scale, which is logarithmic. 30 decibels for a whisper, 140 for a jet engine. Every time the decibel number increases by 10, the actual sound pressure increases by 10 times. We see the same compression in chemistry. This scale displays pH, plotting hydrogen ion concentration. Your blood maintains a strict pH of 7.4. A drop to 7.0 is life-threatening. That shift of just 0.4 represents a 2.5 times increase in actual blood acidity. These logarithmic scales are not just convenient, they match how our bodies actually perceive the world. They align mathematical measurement with biological perception. Let us connect this back to the math. If A is 10 to the power of m and B is 10 to the power of n, how do you find the logarithm of A multiplied by B? Pause the video. Use what you know about exponents to find the answer. When you multiply 10 to the m and 10 to the n, you add the exponents. You get 10 to the power of m plus n. Because the logarithm is just the exponent, the log of a times b is simply m plus n. That gives us log a plus log b. Multiplication becomes addition. Base 10 is useful for counting digits, but nature rarely grows in discrete steps of 10. Systems that grow continuously, like a population or an investment, grow at a rate proportional to their current size. This smooth growth is defined by the number e. To measure the cycles of that growth, we use the natural logarithm. The natural logarithm has an exact geometric definition. Draw the curve for 1 over x. Find the area under this curve from 1 to t. That area equals the natural logarithm of t. This integral demonstrates the core link between logarithms and calculus. The logarithm is the bridge between two worlds. It converts the overwhelming exponential reality of the universe into a linear scale we can actually understand. That power was waiting behind a single calculator button the whole time.